Hi, I got an excellent response from the previous blog on the Gaussian resistor distribution and measurement and how you can expect, what can you expect from a plus minus 1% tolerance resistor. And there were quite a lot of people asking me to do more measurements to get some, another brand of resistor that, a cheap OneHungLow brand type, and also 1% metal film, same as last time, but a different brand instead of a good quality Philips one. What would be the result? Good question. And also get a 5% carbon film one and see what would happen, and a whole bunch of other things. So I've done just that. Here we go. I've got a couple of boxes of 5% carbon film and 1% metal film, and yes, they are direct from genuine from the OneHungLow factory in China. Let's go. And the other thing I thought I'd do is kind of semi-automate, or try and automate as much as possible, the process of measuring and logging this data, because before I just used some alligator clips and I hooked it up and I read the value off the multimeter, I typed in the spreadsheet, press enter, disconnect, reconnect to the next one, and well, it wasn't that much fun. Now I've got a box of 1,000 resistors. I'm going to hopefully try and do 1,000 of each type. That's 2,000 resistors. Not going to use these leads. I think I'll spend at least an hour or two just jury rigging something, see if I can get something semi-automated. And these are the resistors we're going to be measuring today. Genuine OneHungLow. I love it. And here we go. There's 1,000 bandoliered 1% 50 ppm metal film resistors. And we've got, and just to represent their lower quality, plain cardboard case, of course, direct from the factory. We've got our 5% tolerance carbon films, 3-band, and they're both 1K, of course, exactly the same as before. I thought I'd keep that consistent. So there you go. Let's give these things a go. And of course, one of the first ideas that sprung to mind to automate this thing was some sort of feed mechanism with guide rails top and bottom like this, thin little guide rails that kept them positioned and sliding through some sort of jig like that, and then some sort of probe which either pushed down on top, so you would pull it through one extra resistor, you'd push down the probes onto the top, and then you'd move it along and so forth. But the problem with that is that unless you actually go to the trouble to add like up motors and rollers to actually advance this thing a certain amount, you've got to do it by hand, you've got to do it by eye anyway, and you've got to, and it's almost a two-step process. If you pull it through and then push it down, something like that, then you've got two hands on that operation. How are you going to push some button to enter the data in if you have to do that or something like that? And then I had the idea, not of a push down one, but I had a similar idea, maybe using some battery spring terminals or these hangers even, something like that, where these sat in some sort of jig. Instead of pushing down, they would, and you would pull it through like that, and it would make contact like that, but the surface isn't that great, and you've got to rely on the tension of the resistor, and it can pull out and it can short to the ones next to it, and it was all messy. I didn't really like that approach at all, and it just seemed too complicated. So unless I did actually go to the trouble to physically automate the thing with a hydraulic thing that comes down, and motors which advance it, and they know the average distance, and it can step it through and stuff like that, it probably wasn't worthwhile. You're probably better off just doing it by hand, especially when you just got like a one-off situation like this. And this is actually quite common in the industry. If you're a beginner or you're studying and you wonder what some of the common things you do in the industry, well, building custom test jigs like this is one of them. You'll find it's very common. I've built countless ones over the years, over the decades, to test various things, test concepts, test PCBs, and all sorts of stuff. So building up jigs like this and having to automate them is a skill which you're probably going to need sooner or later in electronics engineering. But anyway, I decided to simplify it and just do a hand-based system. So let's take a look at that. And this is what we're going to use today. We're going to use what's called a pogo pin. And these are like an industry standard way to build PCB test jigs and things like that. They're really great. And as you can see, they actually plunge down like that. So they're also called plungers. So if you search for like a plunger pin or something like that, or a serrated plunger, as we got here, you can see that on the tip of it there is actually all these little serrated, jaggy, sharp points. And you can get many different types. You can get ones with a single sharp point that are designed to penetrate oxide on a PCB. In this case, it's multiple sharp points, which is exactly what we want for going on to a resistor test lead, I think. You can get ones that are concave as well, like they go over test posts and things like that. In this case, the one we've got here is the it's from Farnell/Element 14. There it is. It's a serrated plunger, and they're quite cheap. They're only $1 each or $2 each, and they're available in many different types, many different widths as well. This is a 1.6 millimeter wide one, so you drill a 1.6 millimeter hole or a 1.5 millimeter hole in your whatever you're using as the basis for your test jig, be it a piece of clear acrylic, Delrin, or any type of those engineering materials. But what we're going to use today is just this little prototyping board, and hopefully we're going to install these on here so that we can actually get just a nice little hand just a little hand press board that allows us to press down onto the pins. Now, normally you would drill, you would use it like this is a board as a template, and the pin would, you'd drill out a certain size hole, and then you'd put it through like that, and you'd glue it in place, and then you can do all sorts of clamp mechanisms. And I've showed examples of these PCB test beds before, but in this case, we want a hand-based test so that we can just push down with our hand onto the resistor pin. Now, the problem with this is that it can, because it's got those serrated pins on the top there, once it bites down on there, it's pretty good. It's not going to slide off, okay? If you got one with a single point, of course, that won't work, but these serrated ones work nicely, and even if you get it sort of on the edge, it's still going to bite in there nicely like that. They are actually really very nice, and they do a really good job of biting on to that lead. And because they're very sharp, they've got very sharp serrated jaws on there, then it should bite through the oxide, any oxide on these resistor leads. And trust me, there is going to be oxide even on brand new resistors. You're still going to get that, so you've got to avoid that. So this is probably an ideal plunger / pogo pin for this application, but unfortunately it's not big enough. Ideally I'd want like a real huge thing. So because this is aligned by hand, it's not some automated machine, ideally I'd like a big 5mm diameter one like that. You just get bang, even Stevie Wonder could probe this thing. But because this has only got a 2mm head on it, it is possible to miss it like that, and that can be really annoying. It can ruin your day and waste a lot of time. So what I'm going to do is widen that to a 4mm pogo pin. I'm going to solder a couple of pins together like this, and then bang, even if you miss one of them, you're still going to get at least one. And if you get both on there at the same time, of course, then you're going to have both come down. But I think that's going to work pretty good, and there's a fair good margin for error there when you press that down. So let's try and use 2 pogo pins each side. Now, it just so happens that this board is, I think, quite a nice width for this particular job. So if we put 2 pins on one end of the board and then 2 pins up on the other end of the board, then that's a fairly good distance. You don't want to get right into the resistor, because if you've got the thing laying on the bench like this, there's going to be the resistors actually, because the body is thicker than the lead, it's you don't want to probe it right in there like that. You want to probe it out here where it's flat on the bench. So I think we'll just put 2 pins on this side and 2 pins on that side, and it'll be hunky-dory. Now, we can't lay them flat, of course, like that, because if we laid them flat, then obviously they're the wrong orientation. They'd be like that. We want to flip it 90 degrees like that. So I'm going to tack two together like I've done here, put it on there, strap it down in there, and strap it through those holes, which are nice. If we line it up, say there, we can strap it through this hole up here on the top, like that, strap it through that hole, and strap it through the hole on the other side of it, hold it in place, put a buttload of solder on there, and it should hold it really quite firmly. And here's our completed board. I think it worked out quite well. You see I've put those pins on vertically like that. I've put two straps up here like this on the ends here and soldered them on the front, and that should be reasonably robust and should last for a fair number of test actuations, I guess. And all I do is hold it like this. It's not bad. Hold it in one hand and I can just go press like that, and each resistor I can just go along, bang, 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 like that. I've got to be careful, of course, not to have my fingers too far down so that they're touching these terminals here. I could strap that with some tape just to make sure. In fact, I probably will strap the whole thing with tape, and then bang, 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 I can go along like that. Brilliant. I love it. And here's the completed unit wrapped up in tape. I've got some reasonable length leads on here, about a foot long, just for flexibility, into 4mm banana plugs, and I can't accidentally touch those pins, so there's no question about that. And I rather like that. It works quite well. But let's test the repeatability of it, shall we? So I'm going to probe a resistor here. Bang, there we go, 1.0003K, and let's wiggle that around, jiggle it like that, probe it again, same resistor, right up the top end, bang, bang, only light amount of pressure, tiny amount of pressure, and it looks like that does a really excellent slide along, does a superb job, more than repeatable, very happy with that. So, part one solved. We've got a semi-automated way to probe our resistors. Beautiful. Not as efficient as a fully automated one, but it's going to save a hell of a lot of time having to unclip and then reclip two alligator clips onto each resistor. If you've got 1,000 resistors or something, that's just crazy. So this should help automate that. The second part of it, we need to automate the actual measurement, or once again, semi-automate this measurement. Now, ideally, I'd like to use my HP 3478A, which we used last time, because it's the highest precision, highest resolution instrument I've got in the lab here. But unfortunately, it's only got a old school GPIB interface there, and well, I don't have any GPIB cards anymore. I've probably got an old ISA card somewhere, but I don't have a computer that has an ISA port anymore. Crazy. So we're going to have to ditch the 3478A, bummer, and we're going to have to use a data logging multimeter. So I thought I'd use the Agilent U1272A. Now, whether or not we use a handheld multimeter like the U1272A or the HP 3478A bench meter, the process is pretty much the same. You want to connect it up to the PC, and you want the PC to automate the measurements. Now, in this case, ideally, what I'd want is for every time that I push this down onto the resistor, I would like for the software to automatically sense that I've probed the resistor, waits for the reading to stabilize, takes the measurement, saves it to the Excel file, and then doesn't take another measurement until I physically disconnect it and it measures an open, and then it starts measuring the next resistor, and then so I don't have to actually press any keys, because the thing that took up all the time last time was pressing the keys. Of course, I'd have to hook on the alligator clips, I'd have to read the measurement, type it in, press enter into the Excel spreadsheet, and make sure I got it right too. So, prone to human error there. But ideally, I want the software to just bang, auto sense that it can do that. Now, I've looked at the software for this, the U1272A, the Agilent data logging software, and it doesn't seem to have the capability. I can upload the measurement results from this. I can start data logging measurements and stuff like that with time intervals and triggers. But yeah, it doesn't really do what I want. But, here's where I don't have to muck around. Oh, sure. Okay, I could write my own software, right? I could, write a little Visual Basic program or whatever, some script which talked to the commands and issued them and did all that. But I don't want to waste my time. I just want to take some measurements and plot some data. So this thing has got 10,000 sample memory built in. So if you only want to measure 1,000 resistors, not a problem. We can push each one, press the button, bang, store, like that. So let's give that a go. Now the U1272A actually has 3 different data logging modes, and we can get into it here by pressing the setup and going into the D-log or data logging menu like this. Now we can then select which data logging mode we want. Trig, we can do hand mode, or we can do auto mode. Now the hand mode sounds like the one we want. That's basically where you manually push a button to store each measurement. But there's always a trap. If you read the manual, it tells you that's only got, for some bizarre reason, 100 sample memory, 100 samples in this mode, not the full 10,000. Crazy. I don't know why. It doesn't tell you why. So if we look at the other modes, auto mode is like an automated time interval. So it'll take 1 sample every second, or once per minute, or once per hour, or something like that. We don't want that. Obviously, we want to store them manually. So as it turns out, we can go into trigger mode. Now, not what this mode is normally used for is you can set it up so, if it goes over or below a certain threshold or something like that, then it will, like if it finds a new min or max, it will store that event in the data memory. But, well, that's no good. But it also has a mode where exactly the same as the hand mode, where you can just press the hold button here and it will store it in memory. So that's the one we want. We'll use that. We'll select that, and we'll go out of there and we'll try and sample this into memory. And we'll start data logging by holding down the log button here. And as you can see, it popped up with the first event there. It pops back to the temperature there. I don't know why. I don't know how to get it to stay exactly on that thing, but as you can see, it's got log written up there. And let's probe our first resistor. Any resistor, doesn't matter. And let's press the trig auto hold button down here. That's pretty stable. And bang, it's we're on trig auto hold mode now. And if we press it once, bang, we've stored it in, and as you can see, it's automatically jumped to number 2. So we get the next resistor here, and we press it again, bang, it automatically settles the reading and jumps to number 3. It really is quite nice. And as you can see, 4, 5, and we can go along, and bang, that is really quite neat. We just press a button, probe, press, and everything's happy. Now, if we go out of log mode, once we're finished, assuming we've done, say, 1,000 resistors or something like that, we can go into view mode by holding down view down here. And as you can see, it's got 7 events, and we can toggle through those events, bang, that we measured. There we go. The first one was open. I don't know what it did there, but the second one, bang, 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 and there you go. And we can upload that data later. Once we've done our 500 or 1,000 resistors, we can upload that to the PC, save it to an Excel file. Nice. It looks like we've eliminated a fair bit of time, not only and potential operator error by typing in the values manually into the spreadsheet. All we got to do is push a button to store it. And you know what I've discovered? I was going to use this trig hold mode where you have to push the button, but I found that you don't. You can actually use the auto hold mode in log mode. I'll show you. Watch this, okay? Well, let's reset it. And this is absolutely brilliant. I won't have to push any buttons. Watch this. Go into log mode, okay? I'm still up to event 12, but, we can start from event 1. And we hold down trig hold mode, and we're in auto hold, not trig hold mode. And if we go in here, and we just push it on there, it takes the stable reading, and then it automatically, you saw that, it logged it in to the next event. And let's probe the next resistor. Bang, 14. There we go. And take it off, disconnect, 15. It automatically is logging and storing each resistor. I think it's brilliant, but it seems if you do it too quickly, it doesn't do it. Like if I go between that one and that one, it hasn't had time, so I'll leave it off a bit. And there we go, it stores it again. So you've got to be careful that you are actually logging that event each time, but there you go. This meter's brilliant. It allows us to log these resistors without pushing, automatically, without pushing a single button, without writing any script or software or anything like that. Fantastic. Now, what would make this really perfect is if I could get the damn thing to beep whenever it stored that event in memory. I'm going to have to search through the menus here and see if I can enable some sort of event beep function. And sure enough, Agilent thought of everything. I did have the beep turned off. I went in the setup, turned it back on. I'm in data logging mode, and watch this. I put it on, beep, event 23. And no, I did it too quickly there. That's the only disadvantage to this, is that if you can't do it too quickly, but beep 24, there it is. I don't even have to watch the meter. All I've got to do is listen for the beep, and I know I've captured that resistor. This is just brilliant. It's automation that I've only traditionally seen in software. I love it. And just for a bit of fun, it just so happens that I have a very high precision 0.01% metal foil resistor, 1K. So I thought we'd hook that up and have a look what absolute value we've got. I've nulled that out. I was getting 1K before. It's slightly different now. It is 0.9999. So there you go. It's pretty spot on. Okay, it's not a genuine calibration. It's a transfer standard using a factory resistor. But 0.01% of 1K is 0.1 ohms, or the least significant digit there. So our absolute values are going to be pretty close to spot on. One of the other good things about the U1272A is that it does delta measurement auto ranging as well. As I said, I nulled that out. So I shorted those particular leads out, and I actually, well, if you do it properly, it nulls it out like that, and there you go. But it keeps that on the other ranges too. It doesn't manually range. There you go. It auto ranges up to megohms. Beauty. And of course, before we start, we want to zero this thing out. So let's do it. There we go. I like it. And is it repeatable? Yep, not a problem. Okay, I'm going to do a quick sanity check here just to make sure we're getting repeatable values using the auto hold function. So I'll go 9951. 9956, 9966. Now if we go back through and check them again, let's see if we get repeatable results. 9951, yep. 9956, yep. 60, oh, 66. It's jumped up to 66. There's a 6 differential there. Don't like that at all. That's no good. 75, 74, yeah, we're within 1. I'm happy if we're within 1. Least significant digit here. 75, yep. 659, yep. 61, 59, 64. Yep, okay. So there was only one that was out by 6 least significant digits. Let's do that again. Number 366. Okay, so it looks like it's repeatable again. So I don't know what happened the first time. The first one must have been a bit out. So let's actually get out of auto hold mode there. And yeah, that's exactly what it is. 9966. And if we compare them without auto hold, 51, 56, 66, 75. And wouldn't you know it, I just played back the video to double check that I actually wrote them down wrong. And that third one that was 6 digits out, I said 66, but I actually wrote down 60. Bloody humans. Done. And if you're wondering how long that took, there you go, 25 minutes. And that included the answering the door for the courier guy. I'm actually rather amazed at this jig, actually. I'm really amazed at the efficiency of this setup. I didn't miss a single reading. I didn't get any double readings or whatever when, you know, if I accidentally touched it twice. It just worked every single time. Very impressed. 25 minutes for 1,000 resistors. That's an average of one resistor every 1.5 seconds, and that includes the handling and everything else. I love it. And if you compare that with using the alligator clips I did last time, that was about 7 or 8 seconds per resistor or thereabouts. So this little simple jig with the auto hold function of this meter has gave me a 5-fold increase in testing speed. Beautiful. And now we want to upload the data. I've got the meter connected to the USB port via the USB IR cable, and it installs the driver, and it's just a COM port. In this case, it's COM 14, and we connect to it, and it should show meter connected. Bang, there it is down there. And you can change ranges and do all sorts of jazz like that, but we want the event data login. It's got manual data login, auto, and event, but because we use the event mode, we want to load this data in here, and bang, here it goes. It looks like there's, here we go. Well, it's going to take a while, and here it is. Bang, 1,000 loaded, no problems at all. And there's the data table for all of our results, and we can export that to an CVS file, which then we can load into Excel or OpenOffice. Now, there's one really annoying thing with this Agilent software, and that is the value it actually reads in. Look, it puts 997.50 space M, so milli. Well, you know, okay, whatever. But when it exports that to the CSV file, then when you try and import it, it's not going to import that as a number. It's going to import that as a text string with that M on the end, and that's going to make it really annoying to actually do that. So you've got to eliminate that M from it somehow. And fortunately, you can do that using the space function, so that it actually it actually eliminated that M and put it in its own column, and then it's in this column here you've got the actual data itself. So that's going to work. An absolute treat. Bingo, there we go. We've got the and we can just kill that column there, and we've got our data in this column. Okay, I've loaded the data into the same spreadsheet I used in the previous blog, so I won't go through that again. And as you can see, I've plotted all 1,000 resistors on the x-axis here versus their percentage deviation from the nominal 1K in the center here, plus 1% to minus 1%. And there's two things to note. The first of all is that the spread of the values is around about, you know, that 0.6 value. So it's very similar to that 0.5% sort of variation that we saw on the Philips brand resistors. So it's a similar sort of tightness in spec. But look at this. It is offset. It's clearly offset about negative, say, 0.35 or thereabouts on average through the middle of that. Offset, there's not a single resistor that is above 1K. There you go. That's what we found from these OneHungLow brand resistors. Whereas the Philips ones in the previous blog you saw were pretty much spot on the nominal 1K, and then they deviated either side. But these OneHungLow brand ones show a negative offset. Go figure. And of course, there's actually no problem with that because they're still within the nominal plus minus 1% tolerance. So they're well within it. So not a problem at all. But the problem might come in if you're relying on the fact that the nominal manufacturing mean is going to be centered spot on 1K right in the center there. And maybe you parallel 10 resistors up and you expect some to be high and some to be low, and you want them to average out to a better tolerance resistor. Well, that's not going to be the case this time. They're going to actually average out to a value of around about minus 0.35% from 1K. Something to watch out for. And if we take a look at the probability distribution histogram here, it's a very similar Gaussian type response like we got with the Phillips resistors, pretty much exactly as you'd expect. But look, we've got this little outlier one down here at -1%. There's a few items right out there that have popped their head out, so that's rather curious. And of course, here's the center line. You can see that minus 0.3% or so offset. Now, that's for 21 bins. Now, if we go down here and increase the number of bins, you can see that the center here isn't actually a nice, smooth response as you'd expect. They've, down at this 0.3%, there's a majority, then they've got another 0.35, and then the next bin up goes up again. So it doesn't really follow that classical bell-shaped curve as much, but you could do other bins, but you do get the bell-shaped response up here, so it's near enough. But once again, those little outliers at -1% have just reared their ugly head. There's nothing in there at all, and there's nothing in under well, on the positive side here, there's absolutely not a thing. Once again, you can see the offset, so it's rather curious. And naturally, of course, there are a few people in response to the previous episode were mentioning the fact that I didn't mention standard deviation, and I didn't really want to, I don't really want to get into standard deviation and how that, it was, the response is pretty much what you'd expect if you get what's called a 6 sigma response for 1%, especially if it was centered. If you remember the previous blog, then the odds, basically, the sigma response and how many sigma you design for will basically dictate the probability of getting a resistor or getting a value right out at these limits right out here. And that's probably what Phillips actually designed for. They may have designed for a 6 sigma response for 1% over that range, but you don't really know unless you're actually the manufacturer to know what actual system they put in place. They may have been working to 3 sigma 0.5% instead of 6 sigma 1%, for example. So anyway, if you want to look up standard deviation and sigmas and how it applies to all this statistic stuff, there's better places to learn that than here. But there you go. It's a rather interesting response. So we'll try the 5% tolerance carbon film resistors and see if we get a different response. I think we will. Alright, I'm not a happy little camper. I'm trying to upload my 5% resistor data, and I've tried restarting the program, restarting the meter. The data's definitely in the meter because I can view it in there, but I try and load it up and it just doesn't load anything at all. It's nuts. What's going on? Look, it won't even call up the menu anymore. This is a heap of crap. I don't know what's happening with this bloody software. It's just locked up. Every time it gets to the first, loading in the first data item, it just locks up and then that's it. And you can cancel out of it, then it won't load again. Tried reinstalling the software and doing all sorts of stuff, and it just doesn't work. I don't know. What's going on? Unbelievable. The data is in here. Here it is. Look, there it is. 1,001 samples. If you go back to the first one, there it is. There's the first sample overload. Next one's 2K. I don't know what's going on there, but there you go. There's all the data, and it's in there. Why can't I bloody well extract it out of here? There's nothing I hate worse than tools that don't work. So I've had enough for today. Damn it, I'll finish editing the video, upload it. Sorry, but you don't get to see the 5% resistor data. Send your hate mail to bloody Agilent.